Talking today about collisions, and the easiest kind of collision that we're going to talk about today are totally inelastic, but I'm going to give you an overview first. When I talk about collisions, I'm talking about two objects colliding with one another, coming into contact with one another, and when they do, they exert forces on one another. That's an action-reaction pair. And what do you know about action-reaction pairs?
They're equal but opposite.
And therefore they do what with momentum? Conserve it. That's right. They conserve momentum. So the key here is that our collisions are all going to conserve momentum no matter what kind of collision we're talking about. But we can divide up collisions into a spectrum. One end of the spectrum, which we're going to analyze today, are the totally inelastic collisions. And the other end of the spectrum are the totally elastic collisions. And in the middle, the great middle, are the partially elastic collisions. And what characterizes these is this. The totally elastic collisions are ones in which kinetic energy, notice I didn't say momentum, I said kinetic energy, is also conserved. Also because, of course, momentum is conserved. Kinetic energy is also conserved. And it turns out mathematically that the only way to make that happen is for the objects to bounce off of each other. That's also true for the partially elastic collisions. Objects bounce, but rather than kinetic energy being conserved, instead a percentage of kinetic energy is conserved.
Totally elastic is like not existent.
Right, so totally elastic is in some ways a theoretical construct, but in reality, like for example, if you consider the air molecules in this room bouncing off of one another, which they do very rapidly, the collisions that are there are like 99.999% elastic. So basically elastic. Closer.
Okay, so this question is just slightly beside the point. On notability, is there any way that you can rest your hand on the screen while typing or writing?
It's
That's weird.
You cannot on the smartboard, I know. Totally inelastic collisions are characterized by the objects stick together. And because they stick together, they share a common final velocity. And so a good example of this would be a tackle, right? You have one football player coming this way, then another football player coming this way. One tackles the other, and now they can be considered as one object of combined mass. Okay, let's draw some pictures so we understand what we're talking about here. With a totally inelastic collision, we're going to have some kind of initial situation, maybe like this. And then we're going to have a final situation, and because the objects are stuck together, we're going to treat them as one object of combined mass m1 and 2, m1 plus m2. And just from your physics experience, what would you say is probably the direction of the final velocity? Yeah, it's going to be somehow northeastish. So here's our V final. And that's because in your brain, you've already got an intuitive understanding of conservation of momentum wired up. The momentum of the system before was that way, so the momentum of the system afterwards is that way. That make sense to everybody? With our totally inelastic collision, our totally elastic collisions, we'll have some kind of initial situation, maybe like this. But after collision, the two objects are going to bounce off of each other, and they're going to go off in different directions. Maybe like this.
So we would find like the axis opposite of both.
Something. We're not sure yet how that's going to go. Okay. When we do the analysis, we'll find out. You can imagine it's mathematically more complicated because instead of one velocity to keep track of in the final case, we've got two. So that's going to add to our mathematical complication. We're going to need an extra equation to handle that. Not doing that today. Today, our whole focus is going to be on these totally inelastic collisions. Okay?
So that picture applies for, the picture in red applies for the...
Yep. For the total, and the partially elastic will also look kind of like this. The difference, honestly, is that for partially elastic collisions, the final velocities will have less of an angle. And the angle that they bounce off, we call it scattering angle. And the scattering angle is what physicists use to tell the energies of the particles that come off. So when particle physicists do their thing, they smash particles together, so on and so forth, and then they report out, well, we found a particle with 52 kiloelectron volts of kinetic energy or whatever. The way they found that was actually by measuring scattering angles.
So would totally be inelastic, kind of like Pong.
Pong.
The Atari game Pong. You had the
That would
little
be,
bowl, the little ball in the center, the blue line, the red line, and
Yeah.
you couldn't let it through, and
that's totally elastic.
yeah.
Yes, because the ball has the same amount of kinetic energy coming off as it does. I think you said
That would be great if it just slowed down after a while.
Well, there was a similar game called Breakout, maybe, where you get the ball to stick to your paddle, and then get it to stick, and then take it somewhere and release.
Oh, yeah, you get to hit all the blocks up here.
Yeah.
Yeah, I would like to.
Okay. So I want to do some examples, as much as I can, of a totally inelastic collision, and I want to modify our problem from yesterday. You remember that we had a 150 kilogram football player. He was running with a speed of 3 meters per second. And we'll have him continue to run with a speed of 3 meters per second. Yesterday we had him collide head on. Today we're going to have a right angle collision. He's going to collide with a player running north at 4 meters per second, like so. And this being football, one of them is going to tackle the other, and so the result is that they are going to move off with a common final velocity. And the fact that they share this common final velocity means that we're dealing with a totally inelastic collision. And so the question, we want to pose two different questions. First question that we want to pose is, what is that final common velocity? That's going to turn out to be an easy question. The second question we're going to pose is, what percentage of the kinetic energy is lost in the collision? And that's going to turn out to be a slightly more complicated question, but not too bad. Okay? So we're going to tackle these questions, and the way that we're going to tackle these questions, the first question here is by momentum accounting. We are going to account for the momentum in the initial state and in the final state, and because when these guys react together, their motion changes because of an action-reaction pair, momentum is conserved, and I can set the momentum in the initial state equal to the momentum in the final state, and that's it. That's my equation. That solves the whole thing. So every single collision comes down to momentum accounting. So here we go. Let's do initial. P0. We're doing this for the system, so we're going to add up the momenta of all of the objects in the system, and in this case, that would be these two guys right here. So we have, well, What do you think? He said 150 times 3 and 125 times 4. What did he leave out? He left out direction, didn't he? What does he need to do to represent the velocities correctly? You can do that, but since we're adding, we don't want them in polar form, we want them in rectangular form. What are the rectangular forms for these two velocities? No calculator needed. Read it straight off the diagram.
3, 0.
3 times 0. 3 over and 0 up. And what is the rectangular form for the second velocity? 0, 4. Now, how many of you can get the 3, 0 and the 0, 4 easily? Has anybody lost on that? Okay. How many of you forgot to remember to do that?
Forgot to.
Yep. You want to remember to represent your vectors with as many components as you have dimensions in the problem. Okay? So now that we've got this, then we have 450, 0, plus 0, 500. And this is kilogram meters per second, of course. This is the momentum of the entire system of the two football players taken together. The momentum of the entire system is pointing this way. You see what I'm saying? In other words, this fellow contributes some over, that guy contributes some up, and the whole system together is like that.
What is momentum? What's it equate? Like, doesn't velocity tell you direction? And then.
Ah, yeah, so you notice something. Momentum is always in the same direction as velocity, right?
Mm-hmm.
So here the momentum of the whole system tells us the velocity of the system as a whole object.
So what is a kilogram meters per second? What does the kilogram thing do?
What it does is it tells us the tendency of that system to be moving in that direction.
So then if you suddenly take away mass, it would go faster.
Assuming conservation of momentum, yeah, that's right. Yeah, that's exactly right. You worked a couple of problems in your homework that were the opposite, right? You had a train car moving down the track, and all of a sudden you drop mass into it, and it moves slower as a result. Yeah. Okay. Now, what about the final? The momentum in the final case. What does P final equal to? P is for Philip Park.
150 kilograms plus 125 times V final.
Yeah. Or we can just combine that as 275 times V final. Does everybody see how the momentum accounting process goes? And then you set them equal to each other. Easy peasy. So that we have as our big bad equation P0 equals P final, or 450 comma 500 equals 275 V final. Divide both sides by 275, and when you do, you're dividing each component by 275, so that you get, I think when the, well, work this out. We're going to get final velocity. 0.636?
Yeah, 4 to X.
1.66.
And for the Y? Meters per second. That's exactly right. And please notice that the V final is in exactly the same direction as the P final, it just has a different magnitude. Which is the question we asked. Okay. So finding the V final is a simple matter of momentum accounting. Answering the second question, what percentage of kinetic energy is lost, is slightly more complicated. It's a matter of doing energy accounting. So we're going to go back to our system. And we're going to compute the kinetic energy of the system before the collision and the kinetic energy of the system after the collision. We're going to see whether or not they're equal to one another. Well, kinetic energy is 1/2 mv squared. And remember that when we talk about the v squared in the kinetic energy, we're talking about the speed without regard to direction. So since the speed of the 150 is 3 meters per second in whatever direction, we take the 3 as his speed. And since the speed of the 125 kilogram guy is 4 meters per second, regardless of direction, we take that as the speed. When you add all that together, what do you get? Go.
It's okay, well, why didn't you divide by 2?
Kinetic energy is 1/2 mv squared.
Oh.
Peter, what do you have? He's getting it.
Yes, there you go.
1,675 joules,
I just said it.
which is really interesting because that's equivalent to the amount of energy stored up in like a 170 kilogram object 1 meter off the floor. So that's a lot of energy from that perspective. From the perspective of the amount of energy stored up in food, this is approximately 1/3 of a calorie. That tells you something about food. Okay. Now, how about K final? K final is kind of tricky. Because I can do the mass easy enough, it's the combined mass, but what about the speed? The speed is interesting because what I know is that my velocity vector is 1.62 over and 1.82 up, right?
Triangle.
Yep, that's exactly right. So v squared is 1.62 squared plus 1.82 squared, right? And oh, look at that. I'm looking for v squared anyway, so I might as well just compute that. When I do, magically, I get 6.
Automatically.
Mathematically. So that I can replace v squared with what it is, which is 6. And when you multiply all of that out, I believe you get 825 joules. So what do you think? Was kinetic energy conserved in this collision? No, a whole lot of energy was lost. Where did it go? No, we're not considering any effects of friction. These guys are colliding, might as well be colliding with ice. It's going to go into, it's going to go into heat, deformation of their bodies. A whole lot of as they collide. Mm-hmm. Okay. So what we usually compute from this is the percentage of kinetic energy that is conserved, and the way that we're going to compute that is final over initial. So in this case, that would be 825 over 1675, and when we do, that turns out to be 49 or 0.493. I think that's right, which is 49.3%. In other words, our collision only retained 49.3%, or about half, of the amount of kinetic energy before the collision. And then the percentage of K lost, which is what we asked, is going to be 1 minus that, or 50.507, or 50.7% of the kinetic energy was lost in this collision. Totally inelastic collisions will always lose some kinetic energy. And the amount that is lost is going to depend upon the relative masses of the two, and also the angle that they collide at. But the key step here was computing the B squared with the Pythagorean theorem. That's the slightly tricky part of the process. Comments?
You said also for the tomorrow quiz.
Your quiz tomorrow is going to be on momentum, conservation of momentum, impulse. Conservation of momentum, sure, certainly could include a collision, but I won't ask you to do any of the kinetic energy stuff, because that's really related mostly to our partially elastic and totally elastic motions. Okay?